This video will detail the critical aspects of the Phase 11 Reliability Report, which shows how testing gallium nitride devices to failure demonstrates robustness unmatched by silicon power MOSFETs. The Phase 11 report was prepared by Dr. Robert Strittmatter and his excellent team of reliability scientists. Let's start with a true story. This goes back to World War II, where bomber missions were being flown from England over Germany. Many of those bombers didn't return, but the ones that did return were pretty shot up. They had flak holes in them and bullet holes in them. From this, the engineers made a composite drawing, which you can see here, and all of the damage that was done and all these various bombers were coming in, were put onto this drawing. The engineers were proceeding to reinforce these areas because logically, if you have holes in these areas, you ought to make the outer shield more resistant to those bullets and flak. Well, a Hungarian refugee by the name of Abraham Wald was walking by. He was a mathematician, and he looked at this and he said, "You're doing it all wrong." And what he meant by that was that they had an error in their thinking process because they wanted to improve the planes that survived. What they really should want to do is improve the planes that failed or crashed before they got home. And in order to do that, they should reinforce the areas that didn't have bullet holes. And this is called survivor bias. Abraham Wald went on as a mathematician to create a field of study called survivor bias. And survivor bias is something that the semiconductor industry has. By saying that, what I mean is that the semiconductor industry tries to qualify devices by testing them at one data point, say for example, maximum temperature and maximum voltage. And then, by making sure that no devices fail after a certain period of time, maybe 1,000 hours, they deem the product acceptable. But that is survivor bias, because in doing that, you don't know when or how devices fail. So EPC has embarked on a very aggressive program to determine when and how our devices fail under all stress conditions. And this table is a summary of that. In the left-hand column, we have the stressors. This includes voltage, current and voltage together, high rate of change in voltage and current, temperature, humidity, mechanical stress, thermomechanical stress. These are all the different ways that a device will experience stress. And from that, we found a group of intrinsic failure mechanisms related to these stresses. At times, what we had to do was stress devices well beyond the datasheet limit in order to find that failure mechanism. And we'll talk a little bit about what that means. And in some cases, we've not yet found a mechanism. In the Phase 11 report, we report on several new mechanisms. And it's shown here on the right-hand column. The ones that are green are the ones that are addressed in this Phase 11 report. The ones that have numbers next to them are addressed in references at the end of the report, which are all previous phase reliability reports from EPC that are available on our website. So let's go ahead and look at one of the basic failure mechanisms based on voltage stress on the gate to the source. This is the simplest case, and it's the one with the most concrete answer to it. So this is a good place to start because the answer to this one really helps us understand how this methodology works, and then we can proceed with a few more complicated examples. To start off with, let's look at the structure of our gate to source in our eGaN transistors. To begin with, I'll say that at this time, we've tested 4,639 of these transistors to 1,000 hours at maximum temperature and maximum voltage without a fail. But of course, that's survivor bias. Those gates look like this in cross-section. They looked like it at the beginning of the test, and they look like it at the end of the test. So we really haven't learned anything. But what we can do is take devices well beyond their data sheet and monitor how they fail. The graph on the left shows the probability of a failure on the vertical axis, and on the horizontal axis, the time for that failure. We took groups of about 32 devices each, and we put bias at 8 volts, 8.5 volts, 9 volts, and 9.5 volts on the devices. And we measured exactly when that device exceeded the datasheet limit for the gate and therefore was a failure. And as you can see, the first devices failed with 9.5 volts applied after a very little while, and then more and more devices failed at each voltage. And at 9.5 volts, you can see that by the time we get to about 2,000 seconds, all 32 devices failed. At this point, and with this applied DC voltage, the probability of failure is 100%, or 1.0 on this graph. We did the same test at a higher temperature, and we can see that in the graph on the right where we did just 9 volts and 9.5 volt legs. From this data, we can create these graphs. On the left-hand side, we show the mean time to failure for devices versus gate voltage at two different temperatures. And on the right-hand side, we answer the question, what is the time to failure for a certain percentage of the devices versus gate bias? In this case, we took the automotive qualified EPC 2212 as a representative device. And since all of the gate structures are essentially the same of all of our devices, this is a good representation of what eGaN technology can do today. And in the end, we still need to verify that all these devices behave exactly in the same way. An important thing to note is on the left, we see very little difference in the failure rates at 25C or 120C. In other words, the gates are not very sensitive to temperature. We also notice that as you go to higher gate bias, the failure rate, of course, increases rapidly and the mean time to failure goes down. On the right-hand side, we show that in terms of percentage of failures. We drew a vertical line to show the maximum rating of our devices. That's 6 volts. And you can see the first diagonal green line that says 1 ppm, and that's our prediction when you'll see 1 part per million failures in our gates. Now, if you follow that line up to the dotted line that says 10 years, you'll see that at 10 years, we'd expect 1 part per million fail at approximately 5.25 volts on the gate. So if you put 5.25 volts DC on our gate and you waited 10 years, you'd see approximately 1 part per million failure. Now, this is a very stringent kind of test, and the fact that we rate our device at 6 volts, where at 10 years you would see about 20 ppm failures, is much, much more stringent than the way power MOSFETs are rated. And it's one of the reasons why to this date we've seen no field gate failures in our eGaN FETs. But when we did fail devices, again, by going way beyond datasheet limits, this is what we saw. Here you're seeing a cross-section of the gate and the gate metal and the metal field plate and the dielectric between the metal field plate and the gate metal. And that's exactly where the failure occurred. In fact, all the devices failed in this manner, sometimes on the left side of the gate and sometimes on the right. Nothing in the gallium nitride areas failed on any of these devices. This failure on the left side of the gate shown here is actually through a silicon nitride layer that separates the field plate from the gate metal. By knowing that we have a single failure mechanism, we can have greater confidence that our results are not just believable, but they're a good predictor of what a customer should be able to see and rely on. And it also gives us a good roadmap on how to improve future generation devices. Now let's go to a case that's more complicated and one that certainly has a lot more discussion in the industry, and that's drain source voltage stress and dynamic RDS-on. We'll start off again with the cross-section of the device, and this is what it looks like. For each and every different device cross-section in our lineup of products, we need to do these tests to establish the failure mechanisms and make sure that we're seeing the same single failure mechanism across our entire family of devices. So we've done that, and we do see a single primary failure mechanism from drain source voltage. Now, up to today, we've tested more than 5,000 eGaN FETs, 1,000 hours each at maximum voltage and 150 degrees centigrade without failure. But again, that's survivor bias. All it tells you is that no device failed for any reason, and they all look like this cross-section at the beginning and at the end of the test. However, many people have heard of something called dynamic RDS on, or dynamic on resistance. And this is what it looks like when you measure the on resistance of a device versus time with voltage applied. On the left-hand side, it's just one single device, and we've measured it as time, the on resistance as time goes on. This test is being done at 120 volts and 150 degrees centigrade, but it's on a 100 volt rated device, so we've gone beyond the datasheet limit. Now we've tested many of these devices, and you'll see that on the right-hand side, a larger population shows that there's some variation from device to device. But by measuring these devices, we've noted that we can extrapolate the rate of increase in on resistance, that blue line, because it's quite a straight line on a log plot. And when it crosses the datasheet limit, the red line, that's when we call it a failure. So as in all these tests, we took failure as being something that is no longer meeting datasheet limits, which is much worse than you would see on a normal device under normal conditions. So once again, we took a bunch of devices, in this case the 100 volt EPC 2016C, and we measured the probability of failure on the vertical axis and the time to failure on the horizontal axis. And we did it at rated voltage, 100 volts. Then we also did it well beyond the datasheet limits, all the way up to 130 volts. And you'll see that by extrapolating to when these devices will cross the datasheet, we can create a time to fail. And that's when we put a dot on this curve. Now, when you're at 130 volts, the device actually exceeds datasheet limits very quickly, so you can measure the actual time it crosses the datasheet. When you're at 100 volts, you have to extrapolate when you predict it will cross the datasheet. Those graphs can be translated into these graphs. On the left-hand graph, you have time, the time to failure, for various percentage failure rates. So 0.0001% is 1 part per million, and 1%, of course, you know what that means. And we draw a 20-year line on this graph. And you can see that the 100 volt rating of the EPC 2016C, we would expect that these devices would see less than 1 part per million failure in far more than 20 years, hundreds of years actually. However, if you look at the error bars, you'll see the error bars dip under the 20-year line a little bit to a little less than 10 years, and that's the 90% probability line. So with 90% probability, we can say that you should see about 1 part per million failures at 90 volts DC bias in about 10 years. But on the right-hand side, there's a mystery. If you look at the drain voltage on the horizontal axis and the mean time to failure on the vertical axis, this is showing the rate of failure versus temperature. Note that the 90 degree C line is above the 150 degree C line and the 35 degree C line. In other words, at 90 degrees centigrade, the time to failure is much longer than at lower temperatures or at higher temperatures. We didn't understand that for several years, and that's a mystery that I will solve for you today. To begin to solve this mystery, let's look at what we think is the mechanism of failure. It's well documented that you can generate hot carriers in gallium nitride when electrons are exposed to high electric fields. These electrons get accelerated to a high energy, and it's high enough that they can actually penetrate layers in the device and get trapped. This image is an actual photograph of the photons emitted by hot carriers as they get trapped, and it's in a generation 4 eGaN FET device. And we can zoom in on that. As you can see here, each of the electrons emit a photon as they get trapped, and we image that light in this photograph. We've also overlaid the mask design so we can tell exactly where those electrons are when they're getting trapped. And it turns out It's the point of highest electric field in the device. With this imaging tool, we could actually modulate the voltage of the devices and see when the hot carriers come in and when they don't. Based on that, we designed our new 5th generation devices so that they would be much less susceptible to hot carrier injection induced dynamic RDS on. But let's go back to the story that we had a minute ago, where we applied DC bias on devices in a test called high temperature reverse bias, or HTRB, and let them sit for thousands of hours, and then measured the increase in on resistance. Now, when you heat up a device with just DC bias on it, all you have is a leakage current, and that may be just a few microamps of electrons that are available to become trapped. Well, these graphs that I'm about to show you are actually a very different kind of test. In order to make sure that we can really understand failures from hot carriers, we wanted to generate as many hot carriers as we can and cause devices to fail quickly. So we developed a circuit that actually generates millions and millions of hot carriers by generating a 10 ampere current pulse at the voltage that you see on this graph. So instead of microamperes, you have 10 amps going through the device at 60 volts, 80 volts, 100 volts, 120 volts. And you can see that as you go up to higher voltages, you can actually start to see the resistance increasing. The horizontal axis is time, and the vertical axis is normalized on resistance that's normalized to time 0. The graph on the left is at 25 degrees C. The graph on the right is at 125 degrees C, and here's the essence of the mystery. Why is it that the dynamic on resistance is almost 0 at 125 degrees C with 120 volts on the device? And yet at 25 degrees C, you can see after 10 years about a 40% change in on resistance. And the answer is that hot carriers, as you raise the temperature of the device, bounce around this thermally vibrating lattice and actually can't go as far before they lose their energy to the point where they can't jump into a trap. So hot carriers have less tendency to get trapped at higher temperatures. So now we can go back and solve that mystery. Before, we showed that at 90 degrees C, devices failed less frequently under DC bias compared to either 35 or 150 degrees C. That's because there are two competing effects when you're doing HTRB. One effect is, as you go to higher temperature, you generate a higher and higher leakage current. This leakage current provides the supply of electrons that can get trapped. The second effect is that hot carriers can't travel as far as you go to higher temperatures. So it turns out that as you go to higher temperatures, the temperature effect keeping the hot carriers from getting trapped is more important until you get above 90 degrees C, in which case you're getting more and more leakage current, so there are a higher number of candidates that can get trapped. It also says that when we're doing traditional HTRB testing at maximum temperature and voltage, we're really not testing the devices very well. Let's go to another one. This one is safe operating area. Safe operating area is the combination of voltage and current that a device can withstand without failure. For many years, it's been well known that MOSFETs have a second breakdown characteristic. With MOSFETs, as you go to higher and higher voltages, the safe operating area, as defined as drain current on the vertical axis and drain source voltage on the horizontal axis, has a bend in it. The 45-degree lines that you see on this curve are lines of constant power and do not have any bends in them. With MOSFETs, they can't take constant power because of a secondary breakdown caused by the rapid decrease in threshold voltage with temperature. So to create these graphs, we developed testing so that you can see these green dots, and they are 100 microsecond pulses that passed. In other words, devices survived. And the red circles are where those devices fail. And they all fail above a constant power line. The triangles are for 1 millisecond pulses, and you can see that they all fail well above the constant power line. We've done this for a whole variety of devices, generation 4, generation 5. This happens to be a generation 5 device. Again, the dots are all above the. We did it here for another generation 4 device. Again, the dots are all above the line. We went past the data sheet on all of these. And here's a 200 volt device. Again, the dots are all above the line. So the conclusion can be made that these devices have a very predictable, thermally limited, safe operating area that users can rely on. Now I'm going to show you a new test, and this one's really cool, and that is short circuit testing to failure. For those of you who worked with IGBTs, you know that they are typically short circuit rated. MOSFETs are not, because they don't typically experience a short circuit in their most common applications. Well, we decided to test our eGaN FETs under short circuit conditions. And here's what the curves look like based on the oscillograms from the tests. On the left side, you'll see the drain source voltage over time, and you'll see it going up, 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 up. And on the right-hand side, you'll see the drain current corresponding to each of these steps. And so, of course, the drain current goes up because you have more gate voltage, and therefore the device will accept more current from an unlimited current source that drives the drain source voltage higher and higher. So with 6 volts on the gate and unlimited current available, the drain source voltage actually goes up to about 60 volts, and the drain current is about 60 amperes. So think about that for a moment. You're running, in this case, several tens of amperes through a device at 60 volts. That's kilowatts of power through this 0.8 square millimeter device for 15 microseconds. Here we tried to see how much we can take and how long it takes for them to fail. This is showing you what happens as we go longer and longer with the pulses until these extraordinary conditions cause a failure. The explosions are actually quite loud when that happens. On the left side, you'll see an EPC 2203 that's a generation 4 device with a total area of 0.8 square millimeters. That's very tiny. They have only 2 bumps by 2 bumps. And the reason we picked tiny devices is because they already take an awful lot of current, so we didn't have enough current source for our big devices. Anyway, as you can see, it blows up somewhere around 18 microseconds. On the right-hand side, you'll see a 5th generation EPC 2051. Again, that's a tiny device. It's 2 bumps by 3 bumps, has a total area of 1.2 square millimeters. And again, at about 15 microseconds, you can see that it gives up. Both of these devices have a maximum gate source voltage of 6 volts on them, and the current is unlimited. Now we can look at that in a table. In this case, we measured at which point these devices failed. Again, the EPC 2203 generation 4 on the left, and the EPC 2051 generation 5 is on the right, and we did it both at 5 volts, the recommended drive voltage, and at 6 volts, the maximum voltage that the devices are allowed to take. And that's probably more than anybody is putting on these devices right now. As you can see, the mean time to failure for the EPC 2203 is about 13 microseconds with 6 volts on the gate, and about 20 microseconds with 5 volts on the gate. And you'll notice that the EPC 2051 actually fails a little sooner with 6 volts on the gate, a little longer with the 5 volts on the gate. If you look at the minimum time, you'll see that it's pretty tight distribution for these devices. The minimum is very close to the mean. So I think it's safe to say that the user could feel very comfortable if they had a short circuit protection circuit that clicked in 5 microseconds. No problem. But one thing that we can say about our devices is they're incredibly robust. Take a look at the energy. 50 millijoules is what these devices are taking per square millimeter before they fail. If you look at that in terms of power per unit area, it's about 3 to 5 kilowatts per square millimeter. That's 3 to 5 kilowatts per square millimeter. Some of our devices are 13 square millimeters, so that means that they would be able to take 65 kilowatts of power before failing. Now we did another calculation to show exactly what temperature these devices are getting to when they fail. The Generation 5 devices were actually failing at a higher temperature than the Generation 4. Good news. But the Generation 4 is failing at an extraordinary 800 degrees centigrade. And of course, that's not recommended for operation of these devices, but take a look at how robust these parts are. By the way, our reliability group is now starting to test power MOSFETs, silicon power MOSFETs. So probably in a few weeks, we'll be able to give you an update, putting some silicon MOSFETs on this graph. And my bet is that they don't go up to 800 degrees C, and we'll see if I'm right. We also did pulse current testing. One thing about GaN devices is that they're faster than anything that's ever been before, and therefore you can have higher DIDT and higher DVDTs than any power device experienced in history. Where this is important is in an application such as LiDAR, that's light detection and ranging. So Rob and his team took our LiDAR test board and developed a LiDAR test where we could very frequently pulse devices at very high current and very narrow pulses. So in this case, the current is about 50 amperes and the pulses are about a couple of nanoseconds wide. And we pulsed it at a very high repetition rate. In the graphs on the right, you'll see the peak current, which is about 60 amperes. And we measure the peak current to make sure these devices are still surviving. And it's out past 4.2 trillion cycles, which is a little bit more than the projected automotive lifetime for a LiDAR system. You'll also notice that the pulse width is very stable at somewhat under 2 nanoseconds. So these devices are very, very stable. And again, we test many, many devices, and they're all very stable. We also tested their on resistance and threshold voltage, and you can see they're very flat all the way out past 4.2 trillion cycles. So we have a lot of confidence when we go out there and talk to time of flight or LiDAR customers that these parts are going to withstand whatever they can do for however long they want to do it. We're continuing these tests because we want to have more devices and we want to take them out to multiple lifetimes of cars with this test, and at some point get them to fail so that we can understand the intrinsic failure mechanisms under these extreme conditions. There are also a series of mechanical tests that we can do. We have many planned. We've done some and presented them in previous reliability reports. But in this one, it's the first time that we're reporting shear test results and backside pressure results. Shear test is where you take a little mandrel and you actually go to the side of the device and you put pressure on it until it breaks away from the PC board. And then you measure the shear strength in terms of grams. Now, Mil Standard 883E method 2019 gives minimum recommended die shear strength versus area of the device. These are basically made for packaged devices that have lots of solder area on a PC board. In our case, our smallest device, the EPC2203, has only 4 little bumps. This graph has die shear strength on a log scale in the vertical axis. Various eGaN FETs are on the horizontal axis, arranged from smallest on the left to largest on the right, and we're comfortably above the recommended minimum failure force in all cases. In fact, the largest die is an order of magnitude higher than the recommendation. So it says our devices are very strong when mounted on a PC board. Devices will withstand high vibration and they'll withstand high shock testing without any problems. We also tested the backside force. This is important because people want to know how much force they can put on the heatsink without cracking the die. They also want to know how much force they can use during pick and placing the device from a tape and reel onto the PC board. We've tested a fair number of devices up to 400 psi. This is well beyond where anybody would crank on a heatsink, and it's well beyond any pressure that would be put on the device by a pick and place machine. And as you can see, we have 0 failures. So we need to keep going on this test to find out exactly where they fail, and then we can use that in the future to make sure future devices are as robust as these devices or even better. So what's the result? The most important results are those that the customers see. As of this recording, we now have 123 billion device hours documented use in the field since January 2017 in our key automotive and telecommunication applications. And we have a total of 3 device units that have failed. 3. These 3 device units failed for an extrinsic failure mechanism, a defect in the wafer fab that has since been fixed. No MOSFET has ever come close to this level of field reliability. This video detailed the critical aspects of the Phase 11 reliability report, showing how testing gallium nitride devices to failure demonstrates robustness unmatched by silicon power MOSFETs. The full report is available on our website at epc-co.com.